Okay, but how about the second part? How about differentiability of this function, the kinks, right? Because so far I have proved injectivity, so I have a continuous function, a continuous bijection actually, from gamma to the image, and because we are working with compact sets and so on, this is the inverse has to be continuous as well, so I already have a homeomorphism. That's what I proved when I proved injectivity. But how about differentiability? So this implies that P of gamma is homeomorphic to gamma. But how about a projection with kinks, with corners? How do we prevent corners? And maybe you can already guess. The proof will be very similar. So maybe I could even leave this last part of the proof without touching anything. Let me just touch the beginning.
Maybe with different colors.
Yes. Is it fine if I erase this part? Okay, so here I define y of t to be the difference, and by contradiction, suppose p of x0 dot is 0, 0. So now I'm proving that the projection, that map is actually Z1. By contradiction, let's suppose that the projection of x0 dot, where x0 is any point that I choose on the periodic orbit, is 0, 0. This is equivalent to having a corner. This is the same as saying, what if this projection, this curve in 2 dimensions is not regular, right? Then I define y of t to be, before it was the difference of 2 solutions, but now is x dot of t. What's the differential equation satisfied by y dot? That is x double dot. Is x double dot, maybe, and it's of this form, y t plus bt yt minus 1 again, right? Because x dot is an eigenfunction of the linearization at the periodic solution. Okay, and this is actually smaller than 0. So again, we are in setting 1, and we can define a 0 number for x dot. Okay, and now x dot of 0 is what? Because I am projecting, right? And this is x dot of 0, and this is x dot of minus 1. X dot of 0 is 0. Now x double dot of 0 is, evaluate here, right? This is x double dot of 0 is a0 times x dot of 0, 0, plus b0 times times x dot of minus 1, 0. And I don't have to do anything else. Okay, so with this, we reach again a contradiction, right? So we cannot have the projection of x dot of t is 0 at any point, and the projection is a regular curve, and then ck comes immediately from that. Okay, and then there was one very, very minor thing that we have to check, which is what if I consider 2 different solutions, right? Can you guess the proof by now? If I consider 2 different solutions, 2 different periodic solutions of 2 up there, I will now show you that the intersection, that the 2 projections cannot intersect. Can you guess how the proof works? Let's change colors again. Now, suppose there is an intersection. So we proved so far almost everything. Suppose that px1 0 equals px2 0, where these are the 2 different periodic solutions. Now define y of t equals x1 of t minus x2 of t. Okay, now this guy is again a solution of a linear problem of this form. Why? Because we saw it at the very beginning. Differences of solutions of equation 2 solve an equation of type 1. Okay? Now you can guess that this still holds. And now we have a slight issue. And it's that y of t is not periodic anymore. So I think I got confused at some point when I was writing the notes. Y of t is not periodic, but it's quasi-periodic. So that means that I can sort of get very close to being periodic after n iterates. So there is a slight technical issue that we have to that we can deal with easily by continuity, which is that rather than y t1 plus np equals yt1, now we will have an epsilon here. Okay, but this epsilon can be made arbitrarily small, and then the rest of the proof follows. by choosing an epsilon so small that these two zero numbers are the same. Is everybody happy with that? I mean, it's a bit more delicate, but that's the gist of it. So we have just repeated the same proof 3 times. That's what I'm trying to say. We've taken 2 solutions, compared them. In the comparison, found a double zero. Because there is a double zero, the zero number must drop. But because our solutions were coming very close to one another, the zero number cannot drop. Because I must be able to recover my old zero number by going forward. But the zero number is a non-increasing function. And that way we reach a contradiction. Okay. Until what time? Until when?
Until 3:10.
Until 3:10. Okay, I still have 10 minutes. Very good. So now you can imagine how the proof works in general if instead of saying a periodic solution, I say an omega limit set. Omega limit sets are recurrent. That means that I can still recover zero numbers when I flow forward. If the zero number ever decayed by a strict zero, by a double zero like here, I should be able to recover it back. And that's the reason why a lemma, just like this one here, still works if I exchange the periodic solution gamma with a general omega limit set. There are a few small things that are different. For example, an omega limit set doesn't have to be a single orbit. That means that when I project an omega limit set, I could still get corners coming from several orbits joining together at an angle. This is not forbidden. But otherwise, the idea is the same. Okay. So now that I have showed you this, I can give you the more general theorem. So now I will erase this. Sorry about the mess. And the more general theorem regarding omega limit sets is actually a Poincaré-Bendixson theorem. So who here knows about the Poincaré-Bendixson theorem?
Most of us.
Okay. But do your students know? Okay.
During the break,
Okay, nice.
they say they didn't say they don't understand this. Okay, so I assume that.
They didn't say no, so it's yes. Okay.
Suppose they understand, I don't get any contradictions.
So there is a more general theorem, and it's not mine, and it's a Poincaré-Bendixson theorem, but it's not. It was not written by Poincaré and Bendixson. Okay, let me call it the Poincaré-Bendixson theorem. And this goes back to John Maleparé and George Sell, 96, I think I told you before, right?
Very new.
I was already born, so it's new. Yes, and the Poincaré-Bendixson theorem essentially says the following. Let xt be a bounded solution of 2 for all t positive. So when we talk about omega limit sets, this is an advantage over considering a global attractor. When we talk about omega limit sets, we only have to concern ourselves about forward time direction. So if I pick an initial condition and I look at the solution of, along this for this initial condition of the DDE, then either 1, omega x0 is a single periodic orbit, or 2, for all phi in omega x0, both alpha phi and this is the alpha limit set, which is just the omega limit set, but with Tn going to minus infinity, are equilibria, or belong to the set of equilibria, I guess.
Or you can write consists of equilibria. That's more precise.
Yeah, but I mean, I'm just saying that you could have, in principle, continua of equilibria, right? Why not? Yes. So this is called. Moreover, it also tells you that. Moreover, phi of omega x0 is homeomorphic to omega x0. But I didn't include this as in the original Poincaré-Bendixson theorem because in the Poincaré-Bendixson theorem because this is not related to the Poincaré-Bendixson theorem. So what's this saying? Well, this is giving us all of the possibilities for the forward dynamics of the system, right? Pick an initial condition, let it flow forward. Where do I arrive at? Well, either you arrive at a single periodic orbit, or you arrive at some object, some omega limit set that you don't know very well, but you know that if you pick an initial condition in this set, in this omega limit set, then you can flow it forward and arrive at something in the set of equilibria, and flow it backward, and you will also arrive at something in the set of equilibria. So 1 tells me that maybe if I start with an initial condition here, then I may even self-intersect many times, but at some point I start to look like a periodic orbit. When you project this in 2 dimensions, you look something very crazy at the beginning because you could have chosen any initial condition. But then in the limit, you actually get a J1 Jordan curve, which is the periodic solution that you are converging to. And case 2 involves many different situations. For example, and this is xt equals xt minus 1. All of the equilibria live along the x equals y axis. And now I pick my initial condition, and again, it can do very crazy stuff. But maybe in the limit, it starts to do something like this. And then what I'm seeing is that when I flow forward, my periodic solution, my solution is actually approaching a homoclinic to this point here, which is an equilibrium. And now let's check the theorem. What's it saying? Well, it's saying that this is the omega limit set, right? And now if I pick an initial condition on the omega limit set, and I will use yellow, but yellow is not very different from white, sadly. Maybe I pick my initial condition phi here, I flow it forward, and I arrive at an equilibrium. I flow it backward. Why should I be able to flow it backward, though? Huh? Yes, it goes to the same equilibrium, but why is the prehistory of phi defined? Interesting. Well, it turns out that if you live on the omega limits, it turns out that the omega limit sets are contained in the global attractor. So you have a prehistory. Yes. And it turns out that you can actually go backwards. And yes, in this case, because it's a bit more intricate, it's because the solution semiflow is injective. There will be a single prehistory, and you will actually approach this same equilibrium. Showing that the solution semiflow is injective, I believe, is an exercise. Yes, and there are many other situations. The heteroclinic I that we had before is also a possibility in this delay equation. And then again, you will have something strange here, and then you will start to approach the I. And then the omega limit set of x0 will be the whole I. And you see how corners appear, right? I'm projecting on 2 dimensions, and now I have corners, because the corners come from the angle between the unstable manifold of this equilibrium and the stable manifold along the direction that the orbit is coming from. And yeah, again, we would be in situation 2. And with this, I think we can end this part. And yeah, the next part will be an example.